All right, so we're going to take a look at converting between rectangular forms of equations and polar forms of equations, and then taking a look at some of the graphs of those things, especially the polar forms. As a general rule, when you have a rectangular equation, it's going to be in using variables x and y, and typically the x is the input or viewed as the input, and y is viewed as the output. In polar form, we're going to have variables with r and theta, r being the output and theta being the input. So you input the angle and you get out the radius of the point at that time. So generally speaking here, theta is the input and r is seen as the output. That may not always be the case, but that's generally speaking what we're going to see. So let's start with just our constant functions, and we'll compare these to rectangular constant functions. So take a look at this for a moment. If I had a constant function, or constant equation I should say, like x equals a constant, like 5, we know in rectangular form that's a vertical line going through 5 in the x direction, right? So the graph of that would be a vertical line over here where x is equal to 5 that has an x-intercept of 5, okay? And essentially every point on that graph has an x-coordinate of 5. It's 5 comma something, okay? If we were to look at the y constant, so like y equals -3, well, that's going to be a horizontal line at -3, or with a y-intercept of -3. Okay, and that's because all of the points on that line have a y-coordinate of -3. Okay, so it would be like it would be like x comma -3, I guess, would be the ordered pair there. So if you relate that to a constant r value, let's say you had an r equal to 3, radius is 3. Well, you're looking for all polar points with a radius of 3, where it would be 3 comma some theta, okay? And so a constant radius of 3, all points with a radius of 3, would just be a circle of radius 3 centered at the origin. Okay, so you get this circle of radius 3 centered at the origin. That is all points of radius 3, no matter the angle. Now, if we were to, and so that's going to be the case for any radius. If you fix a radius, you get a circle centered at the origin. Now, if you were to fix theta, let's say theta is, for instance, pi over 6, right? That would be a 30-degree angle. That was my furnace going off, something. So let's say pi over 6 is a 30-degree angle, and you want a constant value there, okay? So that's going to be every point with a theta with an angle of pi over 6. The radius could be anything, positive, negative, whatever. And so to graph that, a 30-degree angle, you're looking at all points, all points on this line that has a 30-degree angle coming up from the polar axis or the positive x-axis, okay? And so, so you end up with a line. Specifically, if theta is constant, that gives you a line that goes through the origin or the pole, okay? Has to go through the origin. If you shift that line up or down, it's going to change the equation quite significantly, in fact. Okay, so at this point, theta is fixed, so the angle is fixed. All right, so those are our basic constant functions. There are lots of other functions and associated graphs. Let's take a look at what would happen if I were to take a linear equation in rectangular coordinates, something like ax plus by equals c. That's a standard form of a line. And let's see what would happen if I convert that into polar form. Okay, well, the polar form basically replaces the x's and y's with r cos theta and r sine theta respectively. So we have a times r cos theta plus b times r sine theta equals c. Now, because I said generally the theta is the input and r is the output, we generally will try to solve for r. We solve for the output, essentially. So when I look at this equation, I can solve for r by factoring out the common r. There's a common factor here. I pull the r out, and I get a cos theta plus b sine theta equals c. Now, to solve for r, we're going to divide out all the stuff that's in parentheses since it's multiplying the r. So if I divide out a cos theta plus b sine theta on the left and divide that out on the right as well, they'll cancel on the left and we'll have r by itself. R will be c divided by a cos theta plus b sine theta. Right, so any polar equation that's in this form, where you have a constant over constant times cosine plus a constant times sine, that's going to be your linear equation. Okay, so an example, if you have the equation r equals 3 over 2 cos theta plus sine theta, if this was an equation given to you, you would know that it's equivalent to the equation 2x plus y equals 3. Right? So it's a linear equation because the a is 2, the b is 1, and the c is 3, and so you could set that up that way. And then you could plot that pretty easily. Okay? So we can convert between polar and rectangular equations now using our four formulas. Okay. Now sometimes a polar equation is easier. Sometimes the rectangular equation is easier. This is an example where I think the rectangular equation is easier to work with than the polar equation. However, as we saw a little bit ago with circles, the polar form of a circle, let's say r equals 3, well, that one, that's a nice circle of radius 3. And it's centered at the origin. Well, if I wanted to write that in rectangular form, well, this top equation, r squared equals x squared plus y squared, is a good option. Essentially, you plug in the 3 for r, and you get 3 squared equals x squared plus y squared. And then if maybe I rearrange that a little bit, that looks terrible. If I rearrange that a little bit, I might have x squared plus y squared equals 9. Now, if you look at the two equations, the polar form and the rectangular form, clearly I would say the polar form is the simpler of the two. Okay, so there are definitely certain shaped graphs that have sort of a more simple polar form, and some will have a more simple rectangular form. Okay. Okay. Now there are many other types of graphs, many that are more convenient to write in polar form. If you were to shift a circle off of the origin, okay, say I have a circle here and I want to move it to the right, so it's not centered at the origin anymore, it's moved over. And let's say it has a radius of 2, for instance. Okay. Well, that circle can be found using, I shouldn't use r there because that assumes a fixed radius of r. Okay, well, that circle could be found using rectangular form and shifting the graph. So if you think about how we would write that, if you center it at the origin, it would be x squared plus y squared equals 4, right? That's the radius squared. But to shift it over, you actually have to subtract, and because I have that, it had to be shifted over 2 to make that intersect at the origin there. So it'd be x minus 2 squared plus y squared equals 4. So this is actually the rectangular form of that line. X minus 2 squared plus y squared equals 4. The rectangular form is a bit messy. You have both x squared and y squared. You have some stuff inside with the x, and so it's quite messy. However, if I were to convert that to polar form, basically I'm going to take all my x's and y's and convert them to r cos theta and r sine theta. So I'd have r cos theta minus 2 squared plus r sine theta squared equals 4. Okay, now again I want to solve this for r, if possible. So I'm going to maybe expand all of this out. Here I would have r squared cos squared theta minus, when you square this, you double the product of the two terms, so you get 4r cos theta, and then square that, you get plus 4. And then here I'd have plus r squared sine squared theta equals 4. So I'm just expanding each of those terms. Here, this one's a little bit tougher to see, but it is r cos theta minus 2 times r cos theta minus 2, and then distributed. I did all that work kind of in one step rather than writing it all out. Okay, then I look at these and I kind of group things together by term, things that are nice. So like r squared cos squared theta and r squared sine squared theta. Well, they both have r squared, so let's put those together. So I get r squared cos squared theta plus r squared sine squared theta. Then I have the other two terms, which are minus 4 r cos theta plus 4 equals 4. Well, actually, before I even go further than that, I got a plus 4 and a plus 4 on each side. If I were to subtract 4 from both sides of this equation, I can eliminate some terms right away. So let's do that. Let's subtract 4 here. Let's subtract 4 here. Both of those 4's will drop off, and we'll be left with no constants, just a 0 on the right side. At this point, if I pull out the r squared from here, I get r squared times the cosine squared theta plus the sine squared theta. Hopefully this might look familiar. Cos squared plus sine squared is a Pythagorean identity. It's equal to 1. Right, so if this thing is equal to 1, then we just have r squared. Now I'm going to need a little more room. Take it up top. R squared is equal to, oh no, r squared minus, I should say, 4r cos theta equals 0. All right. So now I could, let's see, I could factor out an r from here. So I can say r times r minus 4 cos theta is equal to 0. Now remember, when solving equations like this, if you have factors equal to 0, you can set each factor individually equal to 0, because the only way to get a product equal 0 is for one or two of the factors to be 0. So I could say either r equals 0 or r minus 4 cos theta equals 0. One of those must be true. Well, if r equals 0, that just gives us the point at the origin. That's good. We can use that point. For all the other r values, we have r equals 4 cos theta. Interesting. Okay, so this r value, I'm sorry, this coefficient on the cosine ends up being the square of the radius of that circle. That's kind of interesting. So technically the equation for that circle is this equation, r equals 4 cos theta. Of course, that's only true when the radius is not 0. If the radius is 0, then you just have that one other point there at the origin. Okay, so the whole circle really would include this. And I suppose if theta value, yeah, I'm trying to think how that would work. Yeah, if the r value is 0, I guess this equation, the theta would have to be, I guess you can make that work, as long as theta is an angle that makes cosine equal to 0. What would that be? 90 degrees, or pi over 2. That would give us a cosine value of 0, so the radius would be 0. So you can still make the 0 work out in that one. Okay. Okay, so anyway, that's going to be your equation for the circle. I would, if you were to ask me which of these two forms of the circle is more convenient, r equals 4 cos theta or x minus 2 squared plus y squared equals 4, if I had to choose, I'd choose the polar form. That seems a lot more simple. They give us the exact same graph. Okay, if we were to shift that graph up instead of to the right, then we'd be looking at 4 times the sine of theta rather than 4 times the cosine of theta. So a vertical shift gives you the sine, a horizontal shift gives you the cosine.